some of the most distant galaxies ever found, are forcing astronomers to ask a simple question: how did they grow so fast? When the James Webb Space Telescope began studying the deep universe, it did not just find faint smudges at the edge of visibility. It found galaxies from extremely early cosmic time that looked brighter, heavier, or more developed than many astronomers expected. A galaxy is not a single object. It is a city of stars, gas dust, and dark matter. Building one takes time. Gas has to gather. Stars have to ignite. Exploding stars have to enrich the next generation. So when we detect galaxies from a young universe, we are looking at nature under a severe time limit. It is like finding a busy city where you expected a few campfires. The surprise is not that the city exists. It is how early the lights are on. The basic takeaway is not that the Big Bang is wrong, or that everything scientists knew collapsed overnight. That is not how careful astronomy works. The discovery is more interesting than that. The early universe may have been better at making bright stars than our models assumed. Some galaxies may contain active black holes adding extra light. Some may be smaller or less massive than they first appeared once better measurements come in. But even with those cautions, the pattern matters. Webb has expanded the number of early galaxies astronomers can study, and some of them are genuinely challenging. They suggest the first generations of stars and galaxies may have assembled quickly in crowded pockets of young cosmic structure. That matters because galaxies are the universe's memory. They record how simple hydrogen and helium became planets' chemistry, and eventually observers. The memorable idea is this: the early universe was not empty and slow. It may have been restless, efficient, and surprisingly bright. And to understand why astronomers trust that signal, the next step is the evidence itself. The evidence begins with light that has been traveling almost since cosmic dawn, because space itself expands. Light from very distant galaxies is stretched on its journey to us. Light that began as ultraviolet or visible can arrive at Webb as infrared. That is exactly the kind of light Webb was built to detect. Astronomers first identify candidate early galaxies by their colors. In simple terms, a very distant galaxy can disappear in some wavelengths and appear in others because ancient light has been shifted and filtered by hydrogen between the galaxy and us. That pattern is a clue, not a final verdict. The stronger evidence comes from spectroscopy, instead of treating a galaxy's light as one glow. Spectroscopy spreads it out like listening for notes inside a chord. Certain features reveal how much the light has been stretched that gives astronomers a redshift, which is one of their best tools for estimating cosmic distance and age. This is why scientists are cautious. Some early candidates may move closer in time after better data. Dusty nearby galaxies, intense star-forming regions, or black holes can sometimes imitate part of the signal. The job is to separate the truly ancient objects from convincing imposters. But several Webb discoveries have already been strengthened by follow-up observations. The credibility is not based on one pretty image. It comes from repeated measurements, different instruments, and the fact that the same physical rules explain how the light should behave. What was observed in plain language is ancient starlight stretched by the growth of the universe, carrying clues about galaxies that existed when cosmic history was still young. What remains uncertain is how massive some of those galaxies really are, how quickly they form their stars, and how much hidden black hole activity may be boosting their brightness. That uncertainty is not a weakness, it is the doorway to the next question. If the early universe built bright galaxies so quickly, what was doing the building? That is the bigger question. Webb has opened. A galaxy does not appear fully formed. It grows inside invisible scaffolding made of dark matter. Gas falls into that structure, cools fragments, and forms stars. In the young universe, those steps may have happened in bursts, not in a slow, gentle flow. One possibility is that the first stars formed in dense regions, where gravity had a head start. Another is that early galaxies converted gas into stars more efficiently than many models predicted. A third possibility is that some of the brightness comes from feeding black holes, because hot material near a black hole can shine intensely. None of these answers is confirmed for every object. Different galaxies may have different stories. That is why astronomers are not just collecting distant points of light. They are trying to reconstruct an ecosystem. Stars, gas dust, black holes, and dark matter, all interacting in the first chapters of cosmic time. The next tests are straightforward. In principle, even if they are difficult in practice, scientists will measure more spectra. They will search for chemical fingerprints. They will compare Webb's observations with computer models. They will ask whether the earliest galaxies were truly massive, or whether their light was temporarily boosted by young stars and active centers. Why does this fascinate people? Because it turns the universe into a biography. We are not only asking where galaxies are, we are asking how the first structures learned to shine. The known fact is already astonishing. Telescopes can now study galaxies so distant that their light began its journey before the universe looked anything like it does today. The uncertainty is just as powerful. We do not yet know the exact recipe that made them. And that is the takeaway. Cosmic Dawn was not a blank page. It was the beginning of a story we are only now learning to read.